Welcome to my second video about conservation of energy, and we're going to learn about potential energy of springs today. So here's everything we have so far, right? We learned the concept of work to define energy. We learned the relationship of work to kinetic energy, and we define kinetic energy as 1/2 mv squared. We define changes in potential energy as the negative of the work, and we found one special case of potential energy, MGH, for gravitational potential energy. And then we looked at total energy is equal to the kinetic energy plus potential energy, and we use that to define the concept of conservation of energy. If there's no external forces removing energy from the system, then the total energy would be conserved. So a simple example of that, if I have a baby on a hill, it's a 10 kilogram baby moving at 1 meter per second, and it's sliding on a frictionless surface as shown. And we're asking how fast is the baby going when it reaches the top of the next hill. So this is a situation where we just figure out the total energy initially at point 1 here. So we'll have the total energy at point 1 will be equal to the total energy at point 2. So total energy at point 1 will be the kinetic energy at point 1 plus the potential energy at point 1 will be the kinetic energy at point 2 plus the potential energy at point 2. So all we need is all the information to fill this in. And here's the baby, totally beautiful drawing of a baby at point 2, and we're trying to find how fast it's moving at this point. So let's write it down. So we have 1/2 the mass of the baby times v1 squared plus mgh. So I guess mgh, so it'll be the mass of the baby times g, and the height in this case will be y1, which is given, right? 20 meters. Now we want the kinetic energy at the end. It's going to be 1/2 mv2 squared plus mg times the height at the end. Right, so there's everything we need. Here we have the total energy of the baby at the very beginning. It has an initial speed and initial potential energy, and at the end it has a new speed and a new potential energy. So you notice that here it has more potential energy. So when it gets to here, some of that potential energy will be converted to kinetic energy. So it will be moving faster here than it will here. So all we need to do is solve for V2, right? We want to solve for V2. Solve for this one. So I'm going to flip the equation around a little bit. Let's see. I'm just going to flip the equation. Here's the 1/2 mv2 squared from the right hand side, and here's 1/2 mv1 squared plus mg y1, and then from the other side mg y2. So I flipped the equation and then I moved one term over, and I can divide out I'm going to divide out this thing here, right? I'm going to divide out this from both sides, and then I end up with v2 squared is equal to v1 squared plus, and then I end up with a 2g y1 minus 2g y2, and solve that for v2. It's going to be the square root of v1 squared plus 2g y1 minus y2. I factored out the 2g, and then it's just a matter of plugging all that into the equation. So let's see, we have, if we plug it all in, we get 14.0 meters per second squared, approximately, or meters per second. So if the baby starts moving at about 1 meter per second at this height, if it comes down to here, it'll be moving even faster down here, but then it slows back down as it goes back here. But by the time it reaches here, the baby is moving at 14 meters per second. That is a fast baby. Next, we're going to talk about potential energy stored in a spring. So the definition of potential energy, or a change of potential energy, is the negative of the work, right? So to find the change in potential energy for scrunching or squishing a spring from x initial to x final, you do minus the integral from x initial to x final of the force of a spring. So minus kx, as we saw before. So we have a minus here and a minus here. They cancel out. You pull out that k, and then it's just the integral of x dx. And the integral of x dx is x squared over 2. You plug in the endpoints, and we get that the change in potential energy is 1/2 kx final squared minus 1/2 kx initial squared. So if we use x initial equals 0 for a relaxed spring where it's not stretched in either direction, then our potential energy stored in a spring is 1/2 kx squared. So whenever I squish a spring by any amount, the energy stored in it will be 1/2 kx squared, which will come in handy. So a simple example of that is, let's say I have, a frictionless taco. Compresses a spring by 10 centimeters. So I take this frictionless taco, I push it against this spring, and I compress it by 10 centimeters. So let's write down everything we know according to this diagram, right? We have x initial, or x1, is 10 centimeters, which we'll use as 0.1 meters. We have the mass of the taco here already. It's given as 150 grams, but I'll make it 0.150 kilograms, just like x1 should be 0.100 meters. We have the spring constant, little k, which is 10.0 newtons per meter, right? And we know that it starts at rest. So I push this taco against the spring and then I let it go. How fast is it going after it leaves the spring? So after it leaves the spring, right, here's the taco. After it leaves the spring, what is its final speed? So that's easy. It's a conservation of an energy problem again, right? So we are going to use that. We're going to use E initial equals E final, and then solve for the final speed of the taco. So now, initial is kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So initially, the taco is at rest. So that means since V initial is 0, that's 0. And we only have the potential energy due to the spring. So it's 1/2 k x1 squared. Now at the end, the taco is moving. And so it's going to be 1/2 m, its speed, its kinetic energy at the end. But the spring is no longer compressed because the taco left the spring, so there's no longer any energy. So that's going to be 0. And this is our answer here. So we can simplify this. The halves cancel out. And solving for V2, do a little bit of manipulation here. V2 is going to be equal to k over m square rooted times x1. Solving that. And now we can get the answer for that. So when I plug in k is equal to 10 newtons per meter, I plug in x is equal to 0.1 meters, and I plug in that the mass is 0.150 kilograms, I get a final speed of 0.816 meters per second, or if I want, and I do, 81.6 centimeters per second. So that's the final speed, of our taco. Basically, at the beginning, there was a bunch of energy stored in the spring. All the energy was stored in the spring, and when we released it, the spring converted that energy into kinetic energy of the taco. Okay, so we are going to do another problem where we have a taco at the top of a hill that starts at rest, right? So its initial speed is 0, and it's released, and it slides down the hill, gaining speed. Now, first it asks how fast is it moving when it hits the bottom of the hill. Then it asks how much does it compress the spring before it stops. This is combining all three things, right? Potential energy due to height, kinetic energy due to motion, and potential energy stored in a spring. So everything is coming together. Let's make a list of everything that we know so far. So the mass is 0.150 kilograms. The initial speed is 0. The initial height is 2.00 meters. the final height in both cases. So here I'm labeling the 3 points, right? The initial spot is 1. When it reaches the bottom of the hill, that's 2. And when it's completely compressed the spring, we'll call that 3. So it's at the bottom of the hill in both those cases. And of course we have K, which is right there, 50.0 newtons per meter. So for question A, we're going to use conservation of energy as we often do. So conservation of energy says that the energy at point 1 when it's at the top of the hill is equal to the energy at 2 when it's at the bottom of the hill. So K1 plus U1 equals K2 plus U2. So when it's at the top of the hill, that's right when we let it go, it's not moving, so its kinetic energy is 0. And the only energy it has when it's at the top of the hill is potential energy, right? So that's going to be mgy1. When it reaches the bottom of the hill, its height is 0, so it has no potential energy, and the spring is not even touched yet. So there's no spring potential energy, there's no gravitational potential energy, there's just 1/2 mv2 squared. So solving that for v2, we get that v2 is equal to the square root of 2gy1. And that's easy to calculate that. It's the square root of, 2 times 9.8 times y1, which is 2 meters. And that works out to about 6.26 meters per second. So that is the final speed of, or at least that's the speed at point 2 of our frictionless taco. So now, point B. Here's the interesting thing. How much does it compress the spring before it stops? Okay, so let's just do what we did before. Let's compare the energy at point 1 at the very beginning to the energy at 3. If I wanted to, I could do the energy at 2 and compare it to the energy at 3, but let's do this one. It's another conservation of energy problem. So the kinetic energy at 1 plus the potential energy at 1 is equal to the kinetic energy at 2 plus the potential energy at 2. So here is the important, so this, same as before, at the top of the hill, when we release it, it's at rest, so that's still 0, and the only energy is mgy1, the only potential energy. That's at the top of the hill. Now, when it's completely compressed the spring, okay, we let it go, it slides down until it completely compressed the spring and stops. So since that's the point where it stops, this is also 0, because that's when it stops. But we want to find out how much does it compress the spring, so it's 0 plus, and then 1/2 k, and we'll call this x2. That's the amount spring compression, right? That's how much the spring is compressed. So how much is that? Well, let's solve for x2. So if I solve for x2, I get that x2 is equal to 2 mgy1 over k square rooted. So I just solved that equation, right? I moved the 2 over, divided by k, and took the square root. And now when I plug all the numbers into this, I get 0.34 meters, or about 34.3 centimeters. So that's another example of using conservation of energy, where you have 2 different types of potential energy and kinetic energy at 3 different points, and you can apply potential energy at all these points. Okay, here's another fun one. I have a 5-gram marble, and it is compressed. It's pushed down against a spring so that it compresses the spring by 8 centimeters. And when it is released, it flies up and then it stops 20 meters above the 0 point. So here we're setting y equals 0 to be the point where the spring is not compressed. Then I compress it by 8 centimeters and I let it go, and the marble is bumped up by 20 meters. It goes up by 20 meters. So let's find the spring constant. So let's write down everything we know here. Let's make a note here. So what do we know? We know that the marble has a mass of 5 grams, which is 0.0050 kilograms. We know that the initial height of the marble when it's compressed is 8 centimeters. It's actually minus 0.080 meters, right? That's the That's the initial compression because it pushed it down. I'm going to take up to be positive. We know that its final height is 20 meters. What else do we know? We know its initial speed, so we pushed it down, so we're going to assume that it starts at rest. And if it goes up 20 meters and stop, then its speed at the end is also 0. So that's going to make it nice and easy. And the thing we don't know is our spring constant. And that's what we're trying to find. So using conservation of energy, we can figure all this out. So remember all the equations that we need here. We have the total energy is, kinetic plus potential. We have the kinetic energy equal 1/2 mv squared. And there's two types of potential to deal with here, right? There's the spring, which is 1/2 kx squared, and there's the gravity, which is mgh. So we have a lot of information here. So let's write down our conservation of energy equation. So let's do that here. So E initial equals E final. So let's write down all the possibilities. So there's the initial kinetic energy plus initial spring potential energy plus initial gravitational potential energy. And then at the end, there's K final plus final gravitational potential energy plus final spring potential energy. So a bunch of these are 0, right? It starts at rest. It ends at rest. And the spring is, when the marble reaches the top, there's no spring energy, so it's just that. So we have 1/2 k, and this is y1 squared, right, which is 0.08 centimeters, or minus 0.8 centimeters, plus the gravitational potential energy. So the gravitational potential energy is mg y1, and that's equal to the gravitational potential energy when it's at the top, which is mg y2, and everything else is 0. So we want to know. So let's solve this for k in steps. So we have here 1/2 k y1 squared is equal to, I'm going to move that mg y1 over, and I factor out the mg, I end up with y2 minus y1. So solving for k, which is the spring constant, I get 2 mg over y1 squared times y2 minus y1. And when I plug in all the numbers into that, I get approximately 307 newtons per meter. So that is the strength of this spring for this particular situation. Now let's look at another way we can apply conservation of energy. In certain situations, if we have a situation with friction, we have to deal with the fact that friction is taking energy out of the system. So remember, work is energy transferred to or from a system by means of an external force. So if we take energy out of the system via an external force, such as friction, then there will be energy lost. All right. So for our purposes, it's a slight modification when there's friction, for example. Instead of just E at one point is equal to the energy at another point, there's the energy at one point plus whatever work is done by friction is equal to the energy at another point. So some energy is removed due to some sort of external work. So an example of that would be, of course, a crown sliding on the floor. So if I have a crown here and 2 kilograms moving at 10 meters per second on a surface with no friction, and it's sliding along, minding its own business, and then it hits a rough patch with a coefficient of friction of 0.5, and that rough patch is 1 meter long, and then afterwards it's going to be moving again. And so what we can do is we can use conservation of energy, including this new term here with the work external, to calculate how fast it's moving at the end. I mean, there's a few ways to do this, but let's write down everything we know. Okay, so the mass of the object is 2.00 kilograms. The speed at time 1, or the initial speed, is 10.0 meters per second. There's no potential energy here, right? It's just kinetic energy. So it's a nice simple one. The kinetic coefficient of friction, that's a weird looking K, is 0.500, and the distance that it travels is going to be 1.00 meters. And then what we want to find is at the end, what is V final, or V2? That's our unknown. And we are going to use for this, we're going to use that E initial plus the work done due to the friction, in this case, is equal to E final. So E initial is only kinetic energy. There's no spring, there's no height, it's all at the same location, so it's just going to be 1/2 mv initial squared. And the work due to friction is going to be minus the force of friction. So I'll just represent the force of kinetic friction times the displacement. And I'm saying minus because it's negative, it's taking energy out, is equal to E final, which is 1/2 mv2 squared. So let's see, 1/2 mv1 squared minus, and then this is of course mu kinetic times the normal force times d is equal to 1/2 mv2 squared, 1/2 mv1 squared minus mu kinetic, and the normal force in this case is just m times g times d is equal to 1/2 mv2 squared. So I'd like to solve this equation for V2 and find out how fast it's going at the end. So V2 is going to be equal to V1 squared minus, and let's see, the m's go away, so minus 2 mu k g d, right? Like that. I believe that's everything. And now we can calculate the final speed. And when I plug in all my numbers, I get about 9.5 meters per second. So it's the same as conservation of energy, is that it's just that some of the energy is taken out of the system due to something like friction.